So in the last video, we discussed about epsilon greedy multi-armed bandit algorithm, and then we wrote down the pseudocode that will help us to be able to translate that into valid code in any programming language of your choice. The most important thing here is you understand the concept and you are able to write it in any programming language of your choice. Now, before we begin to see how we can use the MAB epsilon greedy multi-armed bandit algorithm to help this robot perform tasks, I'm going to talk to you about other forms of mechanisms for balancing exploration and exploitation. So we have epsilon greedy with decay and then the softmax selection policy. The difference between epsilon greedy and epsilon greedy with decay is you can see that in the original epsilon greedy, our epsilon is static. We set it to, let's say, 0.1 and it remains 0.1 for the rest of the life of the agent. However, it is not very prudent because at a point, especially in an environment where the distribution of rewards are static, it doesn't make sense after a certain number of trials to keep exploring, because at that point the agent would have learned enough about its environment to know absolutely the best action to take. And in such environment, it is not prudent for you to keep epsilon static. So what you can do is you add another parameter called decay, which is an even smaller number. You can set decay to, let's say, 0.01. And what happens is after every n epochs or after every n trials, you multiply your epsilon by the decay. So your epsilon keeps reducing and reducing and reducing as the agent interacts more with its environment, because basically the agent is performing trials and errors within the environment and using the reward signal from the environment to reinforce its actions. So once it has learned enough about the environment, it doesn't make sense to keep trying things. Okay, so that is it for epsilon decay. For softmax selection, what happens is it uses a softmax to calculate the softmax function, if you know about it, to calculate the action values. And what happens is that it helps you to balance between exploration and exploitation without necessarily having to train or having to figure out what your epsilon or your decay is supposed to be. And because we are not going to use that in this example, I'm not going to explain it, but if you want to know about these two, you can leave your comment and then I can make subsequent videos to explain them properly, because I want to keep things short and then finish faster. Okay, so now we have learned about everything we need now, so it is time for us to go and then build our robot. So if you have your robot already set up, you might be wondering, okay, so how will I let the robot know that I like the action it is taking, or it is doing something that is in line with the purpose for which it has been built? Because as you will see in the code, we are not going to explicitly program the robot to do what we want it to do. However, it will figure out what we want it to do based on how we calculate the reward. So one more important thing to know about in reinforcement learning is something called the reward function. So that is what we use to calculate the reward. In this robot, the reason why we have this infrared sensor here is because, like I stated in some previous section, I said we are going to program this robot to do three things depending on the reward function. We can either program it such that its objective is to get close to the obstacle that has been placed in front of it. So we can put an obstacle in front of it and the robot's job is to go closer to the obstacle. And once it keeps doing that, it gets more rewards. We can also program it such that it has to move further away from the obstacle. And so it will figure out that, oh, okay, I have to move away from this obstacle. And that is also going to be influenced by the reward function that we design. And we can also program the robot that, yes, you have the ability to move forward and back, but at this point in time, we want you to remain stagnant. So what happens is we will penalize the robot if it moves either forward or backward, and we will reward it when it stands still. Okay, so how are we going to calculate, how are we going to implement our reward function? For our robot, let's say this is an obstacle. Okay, so let's say this is a wall. I hope I've drawn it well enough. So I'm trying to draw in 3D something. So let's say this is a wall and our robot is here. Okay, what happens is the infrared sensor shoots an infrared light and then it goes all the way until it bounces back. So for it to bounce back, it needs to hit a solid object. It shouldn't be transparent. When it bounces back, the infrared signal will be reflected back into the sensor, and the sensor is going to measure the time between it shooting the ray and the ray getting back to it to estimate how far away it is from an obstacle. Unfortunately for us, this infrared sensor has a range of just about 100 centimeters, so it's not too long a range, but for the purpose of our demonstration, it will still work fine. So what will happen is we start off by placing the robot in front of an obstacle, okay? And then we design our reward function such that it will have to train the robot to know what we want it to do. So first scenario, we want the robot to get closer and closer and closer to the obstacle that has been placed in front of it. The way we do that is we will first of all start off by measuring the distance between the robot and the obstacle. So let's call that previous distance. Okay? Previous distance is equal to, we read the sensor value. So we read the sensor value. Okay? And then we will use epsilon greedy. So we generate a random number, and if it is less than epsilon, we take a random action. The actions that this robot can perform is to move forward. So move forward, okay, move backwards, or stand still. So we generate a random number, and if the random number is less than epsilon, then we want to take a random action. So what happens is we can choose any of these actions, okay? Now the robot will generate some random number and decide, okay, which action should I take? Let's say it takes the action of moving backward. So when it moves backward, mind you, these actions have been coded not to be continuous. So move forward is actually a step forward. The robot can move just some small distance and stop. It can also move just some small distance backward and it stops, and it can stand still for some time and it stops. Okay, so let's say in the first scenario it moved back. When it moves back, it will measure its distance from the obstacle once more. Okay, so let's say it started off with previous distance being equal to, let's say, 70. Okay, now it moves backward, it measures its distance, and it realizes that the distance is now 72. So we say, okay, our objective is for you to get closer and closer to the object, to the obstacle in front of you. So now that your current distance from the obstacle is bigger than where you started off, it means you've taken the wrong action. So what we do is we penalize it. We can give it a reward of -1. Okay, we can give it a reward of -1. Then the algorithm will go through the loop again. It generates a random number, and then it takes a random action or the best action. It depends on the random number that is generated. So let's say this time the robot moves forward, or it could also be back, but for the sake of explanation, let's say it moves forward. Then it realizes that now it has gone to the point where the distance is 71. So we subtract the current distance from the previous distance, and we realize that, okay, you've gotten closer to the obstacle, and then we give it a reward of +1. It generates a random number again. It goes to, let's say, 69, and it realizes it has moved forward. It gets +1. Mind you, in our calculation of action values, because we will be accumulating these rewards, okay? Cast your mind back to some previous section where I was explaining how to calculate action values. We will be updating the rewards that it has gotten for taking each action, and we'll be re-estimating the action values on every trial. So you see that at a point, it will realize that, okay, it looks like moving closer to this object is what gives me bigger rewards, and so it will keep driving forward and forward and forward and forward just to optimize the the expected return, because it will keep accumulating these ones, adding them up, and that is what will inform it on the decision that it has to take. So let's say we want the robot to stand still. What will happen is, in the same way, it will start at a point, it will move forward or backwards, and then it will measure its new distance. We have to design the reward function. So the reward function will take into consideration the previous distance and the current distance, and we will calculate the difference. And if we see that, if the current distance is bigger than the previous distance, then depending on whether we want it to move forward or back or stand still, we give it a reward, a positive reward if we took the positive action, and we give it a negative reward if we took the negative action. Now, mind you, when it comes to designing these reward function, you don't necessarily always have to give the robot a positive reward. Sometimes the reward could even be 0 for taking the right actions. However, you can give it negative rewards for taking the wrong actions. And because negative is smaller than 0, the robot will still want to optimize to at least maintain the 0 reward that it has, instead of taking the wrong actions and then getting negative rewards. So, I mean, it is purely arbitrary, and you have to apply, let's say, common sense to how you design your reward function. The whole idea is the reward function has to inform the robot on which action is deemed the best and which action is deemed wrong. So basically what is helping us here is the infrared sensor that is going to help us determine where we are, how far away we are from the obstacle, and that value will go into the calculation of our reward. And then we also control these motors to take the action of moving forward or backward or remaining standstill. So this is the end of all the theoretical explanations that you need to be able to understand what is going on. And in the next videos, which is going to be a screencast, I'm going to show you the code, and then we will run it on the robot and see how it performs on the ground. So thank you, and I'll see you later.